thanks to the organizing for giving me the opportunity to present my work with Damien in Paris. And it will be a short talk. I'll get right into it. So, as we've seen today, contextuality and locality are pretty much everywhere when we talk about quantum theory. And we've seen that they're very important, or they seem to have some relationship with speed-ups and computational tasks, or just quantum information in general. So what we decided to do was maybe a little bit the reverse of some of the things we've seen today, which was, okay, there exists this Spekkens toy model, which is a classical, realist, and local theory that reproduces many aspects of quantum mechanics, non-contextuality and non-locality, of course. So can we define some interesting quantum protocols within this model? And the idea is that since the Spekkens toy model is local, any quantum protocol that exists in a toy model shouldn't use the non-locality or contextuality. So what's the toy model? We heard a little bit about it in the past few days. First thing, states. There are some underlying states of reality. That's a discrete set. Your system is always in one of these states. And this represents your local hidden variables. So you can never really access them individually. You cannot manipulate them. You cannot individually prepare them. What you can say, though, are you can describe them statistically. So your description of the system will be an epistemic description. That's why they call it epistemic states. And it represents your knowledge over these hidden variables. In particular, Spekkens' original idea was to impose some restriction on what an observer can know in a state of maximal knowledge in a pure state. And this principle roughly, if you only have one system, you can say that the amount of knowledge you have about your local hidden variable should be matched by the amount of ignorance you have. You can formalize this a little bit better, and an important consequence of this principle is that all of your epistemic states represent uniform distribution over the local hidden variables. This is important because it really makes a link between a stabilizer, the fragment of stabilizer quantum mechanics. So in the case of the qubit stabilizer and the toy stabilizer are very, very similar. They're not identical. There's several results that explore this idea, and the difference between the two it's quite well understood, especially from a categorical approach. However, what we wanted to do here was to talk about protocols, so we thought about working with the actual stabilizer formalism as it was introduced by Marcus a few years ago. I'll go into the details of that later. And what's important to see is that the toy model is a local theory, but is steerable. So the idea of non-classicality here is that until you violate a Bell inequality, there can exist a local hidden variable model that describes what's going on. And another thing which is important to point out is that computationally the toy model is extremely weak. So stabilizers are not very good for performing quantum computation in terms of speed up. So of course we don't expect any speed up to appear in the toy model. So the pictorial way to see the result, we started from the stabilizer nature of the toy model. We added a few additions also in order to be able to talk about more complex protocols. And then we thought about encoding information as a general principle. So how can I encode, let's say, K system onto N physical systems where N is greater? And to do this, if you encode information, then you can start asking questions like, can I do error correction and secret sharing kind of protocols? The toy model, I said, is very similar to quantum mechanics in the sense that it has a no-cloning theorem, so it's not obvious whether you can do that or not. We show that no bit commitment, as one would expect, but in perfect and imperfect situation. And then, since we wanted to talk about blind and verified computation, the very same protocol that Elham and Andrew have been talking about before, we defined a measurement-based model for the toy model, and then we show that you can do blind and verified. I will go through some of these results in more details than others in the next slide. So if you want to see the stabilizer notation for the toy model, Marcuse, for one single system, define these 4 diagonal matrices that represent the states your system can be in. And then everything pretty much proceeds in the same way as you would do quantum. So if you are familiar with the stabilizer, you can think of this as in the quantum case. So you take a subset of the Pauli group, of the Pauli over n systems, such that they all commute and they define a unique state. You can also define it in terms of the generator of the group. Or you can also define it in terms of, in the case of the toy model, a diagonal matrix, which represents the distribution over your local hidden variables. There are furthermore 3 ways that you can evolve your system. The first one is that you can do permutation over this diagonal matrix. Not all permutation are allowed, but you can do so. You can perform measurements. The important aspects of measurement is that so there are partition of your ontic subspace, of your ontic underlying space. There are probabilistic, and you can think about them in the same way that quantum measurements are. And you also, since you want to impose that the resulting state is also a valid state in the theory, they are intrusive operations in the sense that the resulting state has to be compatible with what you just measured and the state that you have measured. And we also introduce a further, we call it generalized transformation, reminiscent of the CPTP map, and it's defined exactly the same way as in the quantum case. The thing that one needs to be careful about is that, of course, this kind of map will usually take you out of the toy model, and you need to be a bit careful in terms of, if I perform a measurement on an ancillary system and then I discard that, what exactly happens and how do I satisfy the knowledge balance principle. In general, we need some of these maps in order to talk about complicated protocols, and we think that in general they don't hinder the nature of the toy model, and they don't introduce any form of contextuality or no locality that will ruin what we wanted to show. So let me very quickly give you an intuition of why toy stabilizers and quantum stabilizers are different. As I said, there are other ways to see this difference, but one is just that, if I take a given state, this is the quantum one, these are the Pauli matrices, and I try to map it to a toy state, I obtain this, and well, this is not a valid toy state. Reason being is that the relation between x and z in the quantum case and the x and z in the toy case is different. So what we propose in order to map states or consider states among the 2 theories is to look at the generators of these stabilizers. And so you can take any quantum state, it has a bunch of generators, and then for each generator I can define a toy generator. I never have any inconsistency here because they're linearly independent, and then I generate some full groups. And when I look at these groups, well, they all orthogonal to each other. So what you say is that to any given quantum state there exists a family of toy states, and all the way around. Another important thing is that in quantum mechanics, operators have a double role. You can both use them to describe your system and to act on the system. In the toy case, that's not the case. So you need to mix the toy observable, the toy stabilizers, and the permutation. Although this seems something trivial, is something that we really need to use if you want to talk about protocols. So again, where are we going? The idea is the existence of a quantum stabilizer protocol. We want to say that it implies the existence of an equivalent toy protocol with equivalent properties. But the word equivalent means whatever the quantum protocol is good at, the toy one should also be. And you can tell right away that in the case of the Mermin square or the GAZ example that we heard about before, this is not going to work, clearly because they are contextual and toy model is not. So the ambiguity really lies in all of this, and what we want to find is we want to find a way to ensure the consistency among the 2 theories. So I'll show you how we prove that there are purifications in the toy model, and that's I think it's a fairly easy way to see how the reasoning goes, and then I will take you through stating the results for the other protocols. So purification, you want to start from a mixed toy state, and you want to find a pure toy state on a larger ensemble, such that when you trace out the reference system, you get back the original mixed state you started off with. In the quantum case, we know that these exist. So what we want to do is we want to find a way such that, we want to say for any toy state you can find some pair of quantum states which have a nice property that we want, and the fact that they have this nice property and the fact that you can go up this way as well will imply the existence of the property in the toy case as well. What you can do is that if you think about stabilizers in general, the only terms where non-vanishing trace is the identity, both in the toy model and in quantum mechanics, if you think about the Pauli group. So you see that when you trace out, for any element, when you trace out on the reference system, it will always, so this term will never survive when it's different from the identity, and it will only survive when it's the identity. So this suggests the idea of, well, when we want to find these two quantum states, we're going to write the generating set for this quantum state to explicitly include the generating set of, of the same form as the one we had over here. And by doing this, basically what we're doing is that we're pushing all of this ambiguity that you have between the two maps in a part of the state that is not relevant for the purpose of the protocol that you want to translate. So the idea is just to try to patch where these problems may arise and try to make a translation across the two theories. So by the existence of purification, then we can also prove the local equivalence. So if I have two purifications of the same state, they are equivalent up to some permutation on the reference system, and then no bit commitment follows pretty much the same way as you get it in quantum mechanics. Error correction is similar, so we want to say that for any quantum error correction code, there exists a toy error correction code, and we also want to say that there is a relationship between error correcting and secret sharing. And what's a bit more surprising in terms of this result is that, well, cloning is not possible in the toy model, just as in quantum mechanics. So we're not expecting that to be the way to go, to do a repetition code. And when you think about graph states, the information is highly non-local in many respects. It's really spread out through your resource. That's how we protect information in quantum information theory. So anyways, the technicality of it really resorting to trying to find a good choice of generators and playing with the syndrome and errors in such a way that you can show that for any good quantum error correcting code, they correspond to a good toy error correcting code. And this brings me to the last protocol I will consider, maybe in time. So you already seen blind and verified computation. The idea is that we have two parties. One is Alice and one is Bob. Alice usually is computationally weak, and she would want to delegate a computation to more powerful Bob. Two properties that you may want are blindness and verification. Blindness means that, although Bob is physically running the computation, he's not able to extract any information from what he's doing. And verify it means that any attempt to cheat or deviate on Bob's side, it's discovered. So the very big question here is, can quantum computation be verified classically? So we don't quite answer this question, of course, but what we look at is contextuality a needed resource for this kind of question? And what's important is that all of these kind of protocols have better than classical properties in most cases. So one class of protocols, like the RUV, references are in the footnote, explicitly uses spell test. So we know that that's not going to work. There's no way to do it. But what about the Fitzsimmons-Kashefi? This one uses graph states, and graph states were defined in the toy model. It uses MBQC, that we can also define for the toy model, and some extra particularities that don't really impose any big problems. So what we do is that by having a similar setup to the quantum one, and having a little extension of the toy model, and when I said before, when you think about the CPTP map and you worry about what can happen, if you think that Gaussian quantum mechanics is also a toy theory, certain of these operations, if you're trying to think maybe an experiment where you're using Gaussian quantum mechanics as your toy model, then you will see that you can motivate them much better than you would for this abstract model. And so our results suggest that the structure of the FK verification protocol is Bell local, it doesn't use contextuality, and that the steering correlations are probably enough. And indeed, one of the results we also saw today is that you can actually try to build a FK protocol which is indeed based on the rigidity of steering. So to conclude, we extend the framework of the stabilizer formalism for the toy model in order to be able to talk about protocols. Despite the classicality and no cloning, we get error correction. We can see a link between the way we encode information in the two theories. And despite the locality, we can still do this blind and verified computation that seems to have some better than classical security features. Other interesting things that one can do is that, well, you can try to look at Gauss and quantum optics and try to define things in that model. That's still a toy model, but it's a more it makes more sense in our world, let's say, than the original toy model. And it will be also interesting to actually find maybe a more general criteria by which you can actually perform this translation of protocols. And so the take-home message for me is that there's a lot of toy stabilizer protocols which are non-trivial, and that should apply for the quantum case as well. And the steering correlations may also be very interesting to do for many applications in quantum information theory. Thank you for listening.
Other questions?
So you said that when you try to construct the toy operations from the stabilizers, you need to add commutations in some way? I didn't quite understand that bit.
So the extra thing we used to...
I think it was in slide 7, so you were talking about...
You mean this ones? The CPP, the toy CPP?
So at some point you said something about going from the stabilizers to operations, and you said you had, I think you had X tilde and Z tilde somewhere. Yes, that one.
Down there.
Yeah.
Okay.
Okay. So could you elaborate on that a little bit?
No. So all I want to say is that if you look at the toy stabilizers, they all commute because they're diagonal matrices. So if you want to recover something that looks like an anticommutation relation, for example, if you do error correction, you do want stabilizer error correction relies on the fact that when you have errors either commute or anticommute, and then you get a syndrome that you can interpret. So all I wanted to say is that this needs to be a little bit added by hand, and if you don't, it's a trivial statement.
So can you put it in a similar way to the way you do it in the stabilizer groups for the toy theory, where you also kind of say something is only a valid stabilizer group if the things satisfy the same commutation relations they would do in the quantum case?
Yeah, so I think actually you can, that's a good point. I think you can also use the tilde version to define a stabilizer group that has the same properties as the other one. Indeed, we actually have, we have two stabilizer equations, one in terms of measurements that you perform. So if I measure something that is in my stabilizer, expectation value is +1, and the other one is about, if I permute a state, if I permute by one of the stabilizer's element, the state is stabilizing, it leaves it invariant.
Right, okay. Yeah.
Yes, sorry.
So I think there are a number of results that say that contextuality is needed for some class or some specific implementation of quantum protocols. And I think I understand that you're saying that for another class that's not the case. I mean, do you understand why or when?
So I think most of the results, at least the ones I'm aware of, contextuality seems to be a very important resource for a computational speeder. When we talk about maybe security and other things, usually, I don't think people usually have the impression that contextuality is the first thing. Of course, if you want to go device independent, and there's a lot of things there where you actually do use Bell inequalities. But so my intuition for the verification is that there are certain protocols where you clearly are using some aspects of non-locality or contextuality in order to achieve what you want to achieve. But maybe there can be other protocols that don't make use of that, or maybe steering is enough. So
I mean, you could equivalently see all of this as just everything's classical, but now I have a limited eavesdropper who can't access my classical data directly, but maybe has just some logical relations on it. So, have you thought about this? Maybe you could think about a whole family of toy-like theories where it's all coming from restricting an eavesdropper.
yeah.
This might be related to some bounded storage model or something.
It could be also interesting to see how having epistemic restrictions in general and what is possible to be known influences what can you do from a cryptographical perspective. We haven't exactly looked into that.